This is systems of linear equations using what's called augmented matrices, and it will lead towards Gaussian methods, which I'll show you. Some other language you'll see, echelon form, row echelon form, etc. But it's a really procedural. This is the gimme question in your exam. It'll be 5, 6 marks maybe. It'll take you a page of work, but it's a bit like proof by induction without step 3. It's just do this, do this, do this, and it works out. So that's where we're at. The first 2 exercises though are just reviews of year 10 and year 11 work with some specifications. We need to just remind ourselves about simultaneous equations. So let's start. And you will note with the work I've said 6A, your selection, whatever you need to do. 6B, I don't think there's many questions there. So I've said all, but again, I'm pretty happy. And 6C is not that many, but again, I'm happy for you to choose. I've done from 6C a good selection of questions. You might choose to make sure you do those. So here's systems of 2 linear equations. You notice they're called systems of linear equations, and because I'm a bit lazy, I'll probably call them SOLE from now on, S-O-L-E. And a system of linear equations looks like this. So we have 2 linear equations in 2 variables. Now we're going to get situations which have 3 equations in 2 variables, or 2 linear equations in 3 variables, or you could get something like 7 linear equations in 10 variables, but obviously in an exam you wouldn't get something like that. And here's an example of a set of 3 linear equations with 3 variables. You may have 2, 3, 4 n variables, you may have 2, 3, 4 n relationships. In your exams, typically you wouldn't go beyond 3 variables or 3 relationships, otherwise it gets a bit out of hand. You may also remember that linear equations can have 0, 1 or an infinite number of solutions. They're the only options. 0, 1 or an infinite number of solutions. And this is going to relate directly back to the stuff we've just been doing, and you'll see that even if there is not a full plane of solutions, there is therefore a line of solutions which is still infinite. So you'll still have an infinite number of solutions. A little reminder here, but this will make more sense once you've done some questions and we've gone through some examples. If there are no solutions, that will come about because of a contradiction in the work. And so you'll get somewhere that 2 equals 7, or that x equals 1 and x equals 6. There'll be some form of contradiction in your working, and that will mean there's no solutions. Often it's a situation where there's more relationships than there are variables. If there's one solution, it will just come out as one single solution and there'll be no other options along the way. And this will work when the relationships equal the number of variables. Not always, but often this is the case. And if there's infinite solutions, it probably means that you have to apply a parameter. And in that case, 1 or more variables cannot be solved for, which usually happens when you have 3 variables and only 2 relationships or something like that. So you can't eliminate enough variables. So let's have a quick look at some examples. And I'd like to do these quickly so I won't take too much of your time. Starting with A, and I'll give you a hint, there's 3 examples, so we can expect to see those 3 situations coming up. So in example A, 2x plus y equals 0 is relationship number 1. Relationship number 2 leads to x equals 3y. And you'll note here that in these there is 2 relationships and 2 variables, so there's almost certainly going to be just a single solution. If x equals 3y, I get 2 times 3y. Oh, sorry, 7, you're right. I was getting ahead of myself. 2 times 3y plus y is equal to 7. Therefore, 7y equals 7, y equals 1, x equals 3. And that works, and we have 1 solution. Any questions about that? That's your simple one. The other 2 aren't too bad, but that's your simple one. So, in question B, we have 3 relationships, but you'll notice here that we only have 2 variables. X minus 2y equals 6, which leads to x is equal to 6 plus 2y. And we'll call this relation number 1. Into relationship number 2, that gives us 3x. Well, I'll just write it down actually. 3x plus y equals 25, which gives us 3 times 6 plus 2y plus y equals 25. And that gives us 18 plus 6y plus y equals 25, which is nice because that gives us 7y equals 7, y equals 1 again. That gives us x is equal to 6 plus 2 times 1, which is 8. Sorry, I'm rushing a little bit, but I'm hoping these two are pretty easy. But there is 3 relationships here, so you should always check that it works in a third. So in relationship number 3 as a verification, negative x plus 3y is equal to negative 8 plus 3 times 1, which is equal to negative 5. But according to this, that should be equal to negative 4. So this is a contradiction. And a contradiction will look like this. One straight line will be there, one straight line will be there. That's line 1 and 2. That gives us the coordinates 1, 8. But the third straight line is just a little bit lower because it's minus 4, not minus 5. Well, actually, it's a little bit higher, but anyway, you get the point. They don't all meet at one point. Do you remember what that's called? If 3 lines meet at one point, do you remember what that's called?
It's called
concurrent if they meet at one point.
Yeah.
Okay. Thank you. Collinear means that they are the same line. So C. C is a set of 2 relationships, 3 variables, so we can expect here for there to be probably no way to solve for all 3 variables, which means you have infinite solutions. So in question C, number 1, actually number 1's a bit harder, let's not do number 1, let's do number 2. In number 2, I get y is equal to 2x. Everybody happy with that? If y is equal to 2x, in number 1, I get x plus 2x plus z is equal to 6. And this means that z is equal to 6 minus 3x. But I don't have enough relationships to eliminate x, y or z, so I don't have enough information. I'm left with this y equals 2x and z equals 3 minus 2x, which means if I let x equal some parameter, lambda, I get x equals lambda, y equals 2 times lambda, and z equals 6 minus 3 times lambda. And this has an infinite number of solutions because it's actually a straight line in the 3 dimensions. And that straight line looks like this. R is equal to, so you might have seen this before, we've talked about this a bit in the past, but you won't have seen it in terms of the variables. 6k plus lambda times I plus 2j minus 3k. So that's the straight line that represents every possible solution. If I want a solution to this relationship, I can say let lambda equal 4. That will mean x equals 4, y equals 8, z equals negative 6 is a solution to this relationship. Is everybody comfortable with that? That's about as tricky as these ones get, but we have less relationships than we have variables, so we can introduce a parameter and we get a straight line of solutions. Example 2. I've actually written the solution here and I was going to rub it off. I wrote the solution when I was testing to see if it actually worked. And I was going to rub it off, but because we're in a bit of a rush, I'm going to leave it there and just talk through the solution, and then you can work through it yourself. So example 2 in blue, for what values of m, n does the following system of linear equations have an infinite number of solutions, 0 solutions, 1 solutions? So remember, an infinite number of solutions will mean that we cannot solve for x and y. 0 solutions will mean that there's a contradiction, and 1 solution will mean that it just works out. So I've gone through my solution here, problem, and said these 2 lines, to have an infinite number of solutions, they have to be the same lines. So I'm looking for them to be parallel, and I'm also looking for them to share a point, so that they are collinear, they're the same lines. Okay? So here I've said the infinite, if they're parallel to start with, 1 has to equal k times equation 2. So 1 is, oh that's right, the x value in 1. So I'm dealing with this x value. To get from the x value in 1 to the x value in 2, I had to multiply by 3.5. So I've said the x value difference is 3.5, and therefore I need my m value to be 3.5 times bigger than the coefficient of y in the first n value to also be a 3.5 multiple of 5. And so m is equal to 3.5, n is equal to 8 3/4 as it turns out. And that gives me that equation 1 is equal to 3.5 times equation 2. So for those very specific m and n values, those two lines are actually the same line, which means we have an infinite number of solutions. 0 solutions if there's a contradiction. So this gives me two lines that are the same, both there. Contradiction if they're two parallel lines, i.e. they never meet, then there is 0 solutions. So that means that m equals negative 3.5, but n doesn't equal 8 3/4, will produce a contradiction. M has to equal negative 3.5 because that produces the same gradient, which means that they are parallel. But then n cannot equal 8 3/4 because that is that translation up that makes it the same line. So if it's anything but 8 3/4, we have a contradiction. And of course, there is one solution. I don't know what the solution is. If m is not, if they're not parallel, which means m cannot be negative 3.5. If they're not parallel, m cannot be negative 3.5. And so the statement here is pertinent. If you're looking for, in systems of two linear equations, an infinite 1 or 0 solutions, you need to consider the ratio between them, whether they're parallel and whether they're the same line. Does anybody have any questions on that one? It's certainly an extension on the first example.